So we're reviewing what we've been going through with chapter 2, where we pretty much discussed limits, looking at limits, one-sided limits, limits exist, where limits go to infinity, negative infinity. We looked at continuity. And so we're reviewing for your exam that you're taking over my math lab this weekend. And the first example gives us a piecewise function. And we have f of x is equal to the equation 0 if x is less than -1. We're given it's 1 over x if x is between 0, the absolute value x, and +1. And it's equal to 0 if x is 1. And the last case is our function is equal to 1 if x is greater than 1. Let's take a moment and let's look at what is this saying when it's 0 is less than the absolute value of x, which is less than 1. And so we have two separate cases here. Let's break this down as two separate inequalities. This is a compound inequality. And so compound inequality, if I break this up into two separate inequalities, then it's an and statement. So I know the absolute value of x has to be greater than 0. And the absolute value of x has to be less than 1. So both of those conditions have to hold true. And means if we're talking about sets, it's the intersection between the two sets. So let's now look at the absolute value of x greater than 0. In order to drop the absolute value of x, we would rewrite this as two separate inequalities. So this would mean that x has to be greater than 0, or means this case or the other case, the absolute value of x has to be less than 0. Well, if that's the case, basically this is saying if this is 0, I can have any value of x that occurs which is less than this. So everything to the left of 0, everything to the right of x equals 0, but not x equals 0 in itself. So that's just for this first inequality. But we also have that the absolute value of x is less than 1. So if you have an absolute value that is less than the number, then we sandwich this in between two of them. So we have -1 is less than x is less than 1. And so if I was looking at this, this is telling me, and I look at the graph of that solution, that's saying that it's everything between -1 and x equals +1, but not including. So we're looking at what do they share in common. So if I look at the piece that they share in common, well, they both have values from -1, not including, all the way to 0, not including, and then from 0 to 1, not including 1. So this piece in here, when we're using that equation 1 over x, we're using it for values that are between -1 and 0, and between 0 and 1. So looking at this, when we're looking at limits and we're looking at continuity, we have to look at limits. So let's look at to see what's going on the left of x equals -1 and the right of x equals -1. Oops, sorry. So let's look at that. So if I'm looking at the limit as x is approaching, and I'm wanting to look at what's happening at the end values of my inequality. So if I'm looking at the limit as x is approaching -1 on the left-hand side, This is telling me these are values of x which are less than -1. And so that would be telling me my function at f of x, I would be using the first equation. And the first equation, so limit as x approaches -1 on the left, would be using the equation of the constant 0. And the limit of a constant is equal to the constant itself, 0. Now let's see what's happening on -1 on the right-hand side. And so if I'm looking at -1 on the right-hand side, that tells me I'm going to use this equation here, 1 over x. So the limit as x approaches -1 on the right-hand side is the equation 1 over x. And if we do direct substitution, I get 1 over -1, which is -1. So right here, I can tell that my limit as x approaches -1 does not exist, because these are not the same values. So if the left and the right are not the same, then the limit as x approaches -1 of f of x does not exist. My y values are different, 0 and -1. To me, then that tells me that we have a jump in our graph. If we have a jump in the graph, then the function is not going to be continuous there. So the function is not continuous at x equals -1. And just from that, it's because of the one condition. 3 conditions have to hold to be continuous. It has to be defined at that value, which it is. If I looked at f of -1, it would be telling me, go into our function, f of x, figure out which equation holds for x equals -1, which is the first equation equals 0. So it does exist. That has to occur for it to be continuous at a value. But the limit has to exist. And right there, we just show that the limit doesn't exist. And so it's not continuous. Okay, so let's look at the limit now as x is approaching 0 on the left and the right. Okay, so let's look at the limit as x approaches 0 on the left-hand side of f of x. So these are values where x is less than 0, but we want to use the piece that it's closest to. And so less than 0, notice we use the equation 1 over x. So the limit as x approaches 0 on the left, we're using the equation 1 over x. So if we plug in 0, or numbers close to 0, so let's say, let's just do this on the side just to show it for a second. So a number close to 0, -0.1. Well, that's the same thing as -10. If I did 1 over -0.01, this is the same thing as -100. So notice as I'm getting closer and closer to 0, so negative, or 1 over -0.001, 1,000ths. This is -1,000. So notice that this is going off to negative infinity. Where if we went in now and looked at the limit as x is approaching 0 on the right-hand side of f of x. So bigger numbers, bigger than 0, notice is also here. Same equation that we're using, but this time we're going to be plugging in numbers to the right of 0. So this is same equation, but now I'm plugging in numbers that are positive, getting closer and closer to 0. And so same idea, but now when I'm plugging in the positive numbers getting closer and closer to 0, this is blowing up. We're going to 1 over 1/10 is 10, 1 over 1/100 is 100. So this is blowing up and going to positive infinity. So limits that don't go to one particular y value don't exist. So these limits actually don't exist, but telling us that it's going to negative and positive infinity helps us know what's going on with a graph. So our limit does not exist. We actually know by looking at 1 over x, it's undefined when x is 0. 0 sets the denominator equal to 0, but not the numerator. So here, we also know that there's a vertical asymptote. At x equals 0. Well, vertical asymptotes, a graph never crosses a vertical asymptote. The function is undefined at x equals 0, except that this is a piecewise function. So it does say we do have a value when x equals 0. I'm sorry, that was not the case. It's actually undefined there. So it's undefined at x equals 0. I thought for some reason they had defined it. At x equals 0. And so it's not continuous at x equals 0. And then I also wanted to, and because it's a vertical asymptote, I can't remove this. This is a non-removable discontinuity. Same thing with the first one that we were looking at, limit as x approaches -1. There was a jump in the graph, and so that's a non-removable discontinuity. The only times that we have a removable continuity is when it's a hole in the graph. And so we can define some point that would close that hole, and then it's now continuous. So let's see what's happening at x equals 1. Okay. So looking at the limit as x is approaching 1, and we want to look at the left-hand side and we want to look at the right-hand side. Let's do a different color. So x is approaching 1 on the left-hand side of f of x. So we want to look at which equation looks at x less than 1, but close to it. And so if we go back to our piecewise function, when we're less than 1, we're going to use 1 over x. So this is equal to the limit as x is approaching 1 on the left of 1 over x. So we're just going to go in and do direct substitution. We get 1 over 1, which is 1. So now let's look at the limit as x is approaching 1 on the right-hand side of f of x. So looking at the piecewise function, we're looking at which equation uses values of x which are greater than 1, but close to it, that equation close to it, and values which are greater than 1 is also equal to 1. So I'm looking at the limit as x approaches 1 on the right of 1, which is 1. So I know my limit exists. And the limit as x approaches 1 of f of x is 1. Okay, my limit exists. In order for it to be continuous, though, f of 1 has to be defined. So if I find f of 1, so I need to go back up here again and look at which equation is defined for x equals 1. Well, if x equals 1, it tells me my graph is 0, or my y value is 0. So this is equal to 0. Notice, in order, again, for a function to be continuous, the limit as x approaches that number has to equal the same thing as f of that number. And this does not equal f of 1. So this is not continuous at x equals 1. So if I defined a point, if we added the point, well, when x is 1, y is 1, that would close that open circle and it would make it continuous at that value. The only problem there is then we now created something that's not a function, because we have something that's coming in on the left where we're equal 1. Let's see. So this is my graph 1 equals my x or my y-axis. This is 1 over x. And I'm coming down, and at 1, I hit a y value of 1. It was open. And then we had one when it was bigger than 1. We were getting back that this was 1, so it's a horizontal line here. But it said when x was 1, we got back 0. So there was a solid circle here. So technically, I could add this point 1, 1. It would make it continuous. The problem is now I don't have a function because it doesn't pass that vertical line test. There's 2 points when x is 1. So I don't know if I can just add that point and say now this is a continuous function, because now it's not a continuous function. But if this point was not defined here, when x was 0, I'm sorry, when x was 1, then if I added that point 1, 1, it's now a continuous function.